I'll be talking today about updates in the paleontology and biostratigraphy, particularly the Cambrian Ordovician units in the Amadeus Basin, and I'll also be discussing a little bit about the surrounding regions because they're important in informing and understanding a little bit about this. This is an update on the stratigraphy as well, so I won't be going into a lot of detail about some of the past work that's been done. But if you want to talk about it, I'm happy to discuss it. There's a lot of work that has been done in the past. And I'll mention it, but there's a lot of it. Before I begin, I suppose I'll probably better introduce some of the groups that I'll be talking about. So, of course, there's trilobites. Trilobites are one of the groups that I've sort of specialized a little bit in. These are fossil arthropods. So they're fossils that people sort of next to dinosaurs are probably most familiar with in terms of fossils. These are fossils that are a bit look like wood lice or cockroaches. Some people think they look a little bit like, but they're not related, not really to either. They're a part of an extinct group. They're only related in the sense that they're all arthropods, so that they're all animals with jointed sort of exoskeletons. Trilobites get their name from the fact that they're divided into three sections or three lobes. And so, for example, trilobites, you can see in this lovely one from Yass here in the center of the image, as well as in the sort of schematic diagrams, they're divided into what's called a central axial lobe that runs down the middle, and then a left and right pleural lobe that's on either side. They're also divided into a head, a body, and a tail, but that's not where the tri in the trilobite comes from. It's the three lobes. Unfortunately, David Attenborough confused that, and in his First Life documentary made the mistake of actually saying it the wrong way around. So correct him next time you listen to David Attenborough's First Life. Now, whilst we'd love to find trilobites as a whole, and there are complete and whole trilobites that you can find in the Amadeus Basin, most trilobites that we find in the field don't look like this. Most trilobites in the field are actually just bits and pieces of trilobites, and that's because when the animal died, and they'd be washed by currents and broken apart, a bit like a crab or even a clam is on the beach. They would break into bits and pieces, or if the animal would molt, which is far more common, they would break up into bits and pieces and be washed about. And so what you're left with is just the remains of the animal as a tiny fragment. And so what we have down here in the right hand, just below that central trilobite, there is just the fragment of a head that's left, what's called the cranidium, which is the central part of the head. So this is just part of the animal. Now, most of the images I'll be showing of trilobites today are of the cranidium, that central part of the head. I tried to sort of make it simplistic and just give that. Of course, you can sort of see different parts of the animal, like we do often figure them as paleontologists when we try and reconstruct these things. But to make it simplistic, I've tried to just keep to the one element to make things sort of a bit easier to sort of comprehend when you're seeing these things. The other group that we deal with in biostratigraphy that's particularly important later on in the Ordovician is conodonts. So conodonts are small little teeth-like elements. People didn't know what they were for a very long time, and up until even into the 80s, they didn't really understand what they were until complete fossils came out, and they could work out that these were the internal teeth of an eel-like animal, which had these large bulging eyes. I love this reconstruction here, partly because it's actually done in a publication, so it wasn't just done as an artistic reconstruction, but somebody put this in a scientific publication, like a screaming mouth, like the scream. And so these are internal teeth of this animal. Now these are animals that probably likely lived in the water column, so we often find these conodonts quite spread out. You don't find them clustered like you would, for example, like a whole trilobite. You find them spread out a bit like the broken up bits of trilobites. So you often, again, have to piece together these bits and pieces to work out what the whole apparatus, what we call the conodont apparatus, would look like. And we can use that because it means that because it spreads out so far and wide, and because these animals are living in the water column, it means that they actually are generally quite well dispersed. So it means that we can work out general connections between different areas based on these fossils. The last group I'll be talking about are brachiopods. There's two groups of brachiopods. There's the rhynchonelliform, or the articulated brachiopods. These are the calcareous ones. And the inarticulate brachiopods. These are brachiopods that don't have a hinge. They're phosphatic ones. The phosphatic ones you can generally get out a bit like the conodonts, and in fact you get them out in the same way out of rock. both conodonts and inarticulate brachiopods, you dissolve the rock, the limestones generally, in acetic acid. And the acetic acid will eat away the carbonate in the rock, but it won't eat away the phosphate that makes up the shells of these inarticulate brachiopods, or the phosphate that makes up the teeth of these conodonts. And so you can produce these quite abundant fossils from just dissolving these rocks in acid. Because they're microscopic, they generally get overlooked in the field. So people will often think that their fields sites are afossiliferous. They'll just walk over the limestones there thinking there's no fossils in them. But in fact, they can actually be quite highly abundant. It's just that you have to take a closer look. So we use these fossils to do what's called biostratigraphy. So a basic sort of overview of biostratigraphy, say you have a field site, for example, this field site over here. So there's just a lovely outcrop of sandstone and limestone. And we have found, in this case, 2 trilobite species here. Now, in the upper trilobite, we can't really compare it to anywhere else. But the trilobite from that lower limestone bed there, we can compare it to one found in another location. Now, if we can compare it to one found in another location, we can compare it to, say, site A here. And then we can also compare it to another one at site B. Now, because fossils themselves can't give us absolute dates, we can't date sedimentary rocks like we can, say, volcanic sequences. We have to use what's called relative dating. So we use the fossils basically as a form of comparative relative forms of dating these forms, these organisms. So we basically just use them as a timestamp, if you like, of between this date and that date, rather than an absolute age on the fossil. In this case, what we can do is we can get these sections, we can compare them against each other, and then create a composite. So we have a global composite sequence over here on the far right. And you can see from the global composite sequence that, in fact, we now have a series of layers with a series of dates. And those series of dates mean that we can actually then say, well, if one of those dates has a trilobite in it, for example, we can give those dates. And so the dates suggest to us that this trilobite that we're looking at here is between 400 and 402 million years old. And so we can use these fossils and relative dating to give a bit of an age range, at least, to a lot of rocks that, in sedimentary rocks cases, we wouldn't be able to date in any other way. So basically, the fossils act as a timestamp. Now, when doing this to the Amadeus Basin, we've got to sort of step back and understand what the Amadeus Basin is. Hopefully, a lot of you know what it is if you're working or living in the Amadeus Basin, or where the Amadeus Basin is. But I'll go through it just in case you're unaware of where or what the Amadeus Basin is. It's a large intercrotonic basin, so it's a basin that sits in the central part of Australia. It's an elongate basin, so it is elongate east to west, and it basically takes up the portion of Australia that sort of ranges from the South Australian Northern Territory border in the south up until about Alice Springs in the north. It goes a little bit beyond that. And then basically from the eastern boundary of the Northern Territory to the western boundary in that sort of border. It goes a little bit into Western Australia as well, but there's not much fossiliferous material on that side. So from a paleontological standpoint, it sort of ends basically at the boundary. When we think of the stratigraphy of the basin, what we see is what we'd generally consider a basic layer cake style stratigraphy. There's a little bit of complexity thrown in there because of different facies. So we have, for example, some carbonates, some siltstones, some sandstones thrown in there because of the complex underlying geology. There's a lot of folding before the basin actually started to form. There's a lot of folding in the basement rock. And so there is a bit of topography that caused quite a differentiation of units into the Cambrian, but a lot of that seems to have basically either disappeared or become sort of filled in much by about the late Cambrian into the Ordovician, where we then get consistent homologous units that seem to cross most of the basin. And we can see this is a basic stratigraphy here. This is one by Giles 2013. And this has largely been repeated as the basic sort of stratigraphy for the basin in most papers, even up until relatively recently. Most papers cite this and or use it, copying it verbatim. And it's based off a lot of the work that was done principally by the geological surveys, particularly Geoscience Australia, what was the BMR at the time, back in the 50s, 60s, and 70s, when they did surveys of the basin. And when they did those surveys of the basin, they generated a lot of the names that you see here for these units. And they gave them rough ages, generally based on preliminary, sometimes paleontological data, but sometimes just lithostratigraphic comparisons. So really, it's a bit of a blank canvas to some extent in terms of actually understanding how these ages are done, because a lot of the time, a lot of their data was unpublished, or it was produced as part of as part of a mapping procedure. It wasn't really done thoroughly and done as descriptive work. It was really done more as just we need to map this quickly and effectively. And so they produced these sort of vague diagrams saying things like early, middle, and late Cambrian, which are terms that don't mean much these days. We don't even use the term early, middle, and late Cambrian, for example, in most Cambrian paleontology these days. They're not formal stage divisions, for example. So to simplify it down a little bit, so because I realize that diagram is A, a little bit fuzzy, and B, it's also a little bit convoluted, I'll simplify it down to sort of the units that are principal interest to what we'll be discussing here. So on the left, you can see the sort of principal units of interest. So these units, as you can see, sort of range from just the base of the top of the the top of the early Cambrian, all the way into possibly breaching into, it said in the last diagram, the late Ordovician. Could be late Ordovician, could be middle Ordovician. It's a bit hard to say because it left it vague in the initial descriptions of these sites. Now, a lot of the fossils that you'll see here, these were fossils that were initially described as part of detailed studies that were done as part of this mapping exercise. The Cambrian was very poorly treated, unfortunately, at least past the earliest most Cambrian. The earliest most Cambrian was treated quite well, as the Todd River Dolostone, and the Akron was treated relatively well. But unfortunately, a lot of the middle Cambrian and late Cambrian wasn't very well studied. Only the latest Cambrian to Ordovician has been documented in some detail by John Sherpold with the Pacoota Sandstone. And then the Horn Valley Siltstone was later published in a significant amount of detail by John Laurie. But most of that, past that, into the Stairway and Stokes, was very, very, very poorly documented as well. Generally based on the fact, in this case, not because it was no hard work was done, just because they're very poorly outcropping. So there's just wasn't a large enough collection of material. So we picked several field sites, and over the years, I've increased the number of field sites I've gone to visit to see these things. Initially, I did a lot of my PhD work around the Ross River Syncline, particularly in Ross River Gorge. For the Cambrian, that's one of the best spots to go to sample this material. But there's also material in the Ferguson ranges. For the Ordovician, the Charlotte ranges, Waterhouse ranges, and James's ranges are also good exposures. And the Gardenia ranges are also rather good for Ordovician material too. So it seems that the depot center for the basin shifted a little bit towards the center into the Ordovician. But in the middle Cambrian in particular, the greater part of the depot center was much towards the northeastern part of the basin. So here's the obligatory field shots. I thought I would chuck in some of the field work photos here and now because I didn't want it to get dry. But here's some of the nice, lovely scenery that we had to drive by to get to these sites. Ross River in particular, when it's flowing, is actually quite beautiful, but you can see here some lovely trace fossils that we found that, whilst not really relevant to the paleontology that we're dealing with, were quite lovely nonetheless. several images on the left there are from the from Ross River Gorge. The one in the top right there is in Roma. I actually have a similar image. Pat Nelson and I are actually in another version of that image. And then down the bottom there is at Malone Creek, which is in the sort of central part of the basin there. So starting off, we decided that we would look at the earliest part. And so when I started really looking at the stratigraphy of the Amadeus Basin and did my PhD, one of the first projects I did was to look at the earliest part of the basin. I'm a bit of a systematic thinker, so I sort of decided to be a bit systematic about this. So I went and started looking at the earliest, or the oldest rocks, if you like, within the basin. So looking at the Tempe Formation, which is a unit that outcrops really only in the central part of the basin. We decided to look at core material for it rather than outcrop material, partly because outcrop is so poor for the material. Unfortunately, because the material in outcrop tends to weather away so quickly, and you're not left with much, not much left much in terms of specimens that you can actually collect out in the field. It generally ends up being covered by a lot of the scree deposits of overlying sandstone units. We ended up using the Hermannsburg 41 core that GA collected as part of the stratigraphic drilling program they had in the 80s. And it was actually fortuitous because it turned out to be highly fossiliferous. We found, for example, a new species of trilobite in amongst it, so Gunniafavia here, as well as several rather important stratigraphically useful brachiopod species. One, for example, what's known as Shizothelian Napuru, and also there's several other species, including Micromitra, and what used to be known as Vandalatrita as well. All these species of brachiopod are all indicative of what's called an Ordian age, which is an age range of what used to be deemed the earliest part of, or the latest part of the early Cambrian, really. It comes from the Zistronera nigrina zone, which is sort of the very, very late part of the early Cambrian. Now, interestingly, the Gunniafavia will come up again, and you'll see it actually occurring in another deposit in a moment that I'll discuss. And it seems that it may actually have some stratigraphic correlation potential in that way. But for now, just it also was a new species that we've discovered in this deposit. So comparing that to the Giles Creek Dolostone, which has often been thought to be a easterly correlate of the Tempe Formation, we collected at the Giles Creek Dolostone as well. The Giles Creek Dolostone you can collect in outcrop. It's a much more resistant unit, and so you can actually physically go and collect. This is obviously at Ross River Gorge. You can see the gorge there in the background. And here, for example, you can see that there's large sequences of limestone and shale interbedded. The interbedded shales, in fact, actually have some very lovely trilobites preserved whole, so you can get near complete specimens found. But a lot of the time, the limestones have most beautifully preserved material, and it tends to be isolated heads and tails of these species. I should mention as well, the arrows in each of my diagrams when I show field sites will indicate the direction up section, so just so you can orient yourself. The Giles Creek Dolostone appeared to also have stratigraphically useful species, but it gave a rather confusing signal. So it gave species like, for example, Zistrodura flifera, which is known from Templetonian, so the earliest part of what was traditionally called the Middle Cambrian, if you like. However, it also gave species like Pagidia silicunda. Now, when we wrote our initial paper, and if you still read our paper on this, you'll read that we interpret this as being a Templetonian species, as being a sort of earliest Middle Cambrian species. But in fact, it turns out that it may in fact be part of the early Cambrian instead, or traditional early Cambrian, one of these Ordian species. And I'll tell you why in a moment. The other thing to note is that we also found 4 new species of trilobite at this deposit. And these 4 new species give you an idea of just the fact that most of the time when we've gone out and collected from the Amadeus, it's actually quite a blank canvas. There is not a lot known about this area. And so every time we've gone out there, we've basically found something new. So I was discussing the fact that we actually now may have got it wrong, and that we've thought that these Pacoota silicunda, for example, were actually Ordovician aged. This comes from the fact that when we were making our comparisons, we were comparing it to a unit known as the Cambrian Formation, particularly a unit called the First Discovery Limestone Member. This is a unit that's not in Central Australia. It's in far western New South Wales, but it's very comparable in many respects to the Giles Creek Dolostone and to some extent the Tempe Formation. It appears to have a lower unit that contains species of Reliquia, which is a definitive early Cambrian Ordovician species of trilobite, as well as agnostids, little tiny sort of trilobite-like animals that are very definitively from the Templetonian. In fact, some of them are the age diagnostic taxa. They're the species that actually give the zones their names. So they're definitively from those periods. So we went out and sampled some of these, and I've collected here myself. You can see here, this is when we were sampling just last year. And it's very hard to sample in this locality because it's largely buried, like the Tempe Formation, but unfortunately no one's cored this. But fortunately, someone did dig a big trench back in the 80s. And that big trench does have material on either side of the trench where they dug it. So we managed to collect some material. And there's a surprising diversity of trilobites in this unit. In fact, it is one of the most, if not the most, diverse trilobite units from this period of time, I would argue. And surprisingly, again, new species, lots of new species. But in amongst those new species, as I said, there was a Reliquia, pinning it definitively, particularly this First Discovery Limestone Member unit, to the early Cambrian. But it also has Pacoota silicunda. So therefore, that species seems to be from the early Middle Cambrian. Sorry, the early part of the latest part of the early Cambrian. But it also contains Gunnia flavia, as well as another one called Zingranaspis cruzii, which we also found in the Tempe Formation. So there's a lot of species that are in common that seem to be below in that lower part of the Giles Creek Dolostone that is shared at the Cambrian Formation with both the Tempe Formation and the lower Giles Creek Dolostone. So this leads me at least to believe that in fact we can sort of separate this into 3 separate assemblages. We have a lower brachiopod assemblage, which crosses over a little bit with some of the trilobites, which seem to range slightly above. And they seem to correlate with some of the Giles Creek Dolostone species that we have. They seem to then, because we don't have those same brachiopod species in the Giles Creek Dolostone, seem to form another assemblage, which we call the Zystrodura gayladia assemblage, because they all contain Zystrodura gayladia. It's one of the most common species in it. And then there's a third assemblage, a higher assemblage in the Giles Creek Dolostone, which appears to be definitively Templetonian, which has Zystrodura foliifera in it. And so therefore we've sort of separated this out into 3 separate assemblages of 3 slightly different ages, all within the Amadeus Basin. So moving further in time, we move into the Shannon Formation. So the Shannon Formation is unfortunately largely afossiliferous throughout most of its exposure. If you travel along from the Giles Creek Dolostone, you actually get quite disappointed as soon as you reach the sort of first beds of the Shannon Formation. It's the unit that directly overlies it. You actually find that it's not very fossiliferous, particularly at its base. It seems like it doesn't contain any fossils at all, really, until you hit right at the top of the unit. And at the top of the unit, there's a little couple of bands. There's 2 bands. They're separated by about approximately 100 to 80 to 100 meters apart. And in that, we find a lot of oolites, as well as large domal stromatolites and herringbone crossbedding, but also thin beds of sandy limestone. And it's those sandy limestone beds that seem to contain trilobites. Now, before we investigated this site, previous to our sort of investigation, there was nothing that was described from these beds. It was reported that trilobites may have occurred there. Erpek in 1967 sort of makes a vague hand-wavy comment saying, I've seen some trilobites in the Ross River Gorge area, sort of at this spot. But he doesn't figure or describe them. He doesn't give much more than just a list of names, basically, and a spot which is very vague. It's basically like turn left at a tree in a creek. And so it's very, very hard to track down where these come from. So going back to the site, we managed to work out exactly where he collected them from. And we managed to find that there was 22 species all up, a lot of which were new. Some of which, for example, include some very strange beasts like this Hebia species down the bottom, which is the first time that genus has ever been recorded in Australia. In fact, it's the first time it's ever been recorded outside of China. So it's a very strange beast, for example. Now, all of this fauna seems to come from what's known as the Glyptognostus Dolostone zone. So it all comes from the latest part of what's known as the Nindialan stage. Now, that's the latest part of what's traditionally called the Middle Cambrian. So we've gone from the earliest part of the Middle Cambrian right until the latest part of the Middle Cambrian, all within that Giles Creek Dolostone to Shannon transition. So huge amount of time represented just by those two units, really. There may be sort of periods in between there of discontinuation. We did see a lot of cryptic disconformities in amongst the basin. There we could trace some of these cryptic disconformities for quite a way. So it suggests that there's probably periods of desiccation within the basin that are previously unrecognized. But it still seems like there's a large chunk of time represented by these two units. Looking slightly above, you can see, and even if you look at sort of Google Earth images of this locality, you can see that there's actually a hillside, and it sort of forms almost like a double hill along the creek. And interestingly enough, if you come to that double hill, the lower part of the hill contains trilobites. And in fact, when Erpek went to first sort of map this, as well as Wells and others, they counted all of this material as being part of the Goiter Formation. However, you can see a distinct difference in both the lithology as well as the paleontology. So that lower unit I was discussing, as I said, had herringbone cross-stratification, had things like, for example, domal stromatolites, had oolites, has fossils in it. As soon as you move above that boundary, you move into a unit that has large mud rip-up clasts, clean dolostones, clean sandstones, and it completely lacks fossils. So it's very lithologically quite different. The only fossils that appear to occur are right up against the boundary between the two units, and they're mostly brachiopods, gastropods, and a few bits and pieces. But even then, they're on the Shannon side of that divide. Now, interestingly, no trilobites seem to cross it, and it seems to be a trilobite extinction event. And that would make sense because it matches well with some of the isotopic data that we get from the site. So this was work done by a colleague of mine in Western Australia. She used some of the data that we collected from several of the localities, one of which was the goiter section that we looked at when we did the Shannon Formation trilobites. And using those, we were able to correlate the Shannon Formation and lower part of the Goiter Formation with other parts of the basin, as well as the Georgina Basin, and what's known as SPICE, which is the Steptonian positive isotope excursion. Now, this Steptonian positive isotope excursion, you might ask, what's that? It's just an isotopic excursion, so where you've basically seen a fractionation of isotopes move in one particular direction compared to a standard. And you can use that to correlate, just like you can use fossils to correlate rocks. And in this case, it correlates it quite well with what would be known as parts of the Ivernian stage and Endemine stage as well. So we can actually date some of these rocks, even though they lack fossils in them. And so what you're looking at here is effectively we can place the lower goiter formation through the entire Endemine stage based purely on the isotopic work. We can also separate out the Shannon Formation into two assemblages. There's the Hadragnostus assemblage and the Amadeus assemblage. One's a lower assemblage, it's slightly lower in the unit, and one's slightly higher, is about 100 meters higher. Of course, there are faunas that cross the two. I should mention that as well. Now, the goiter formation, even in its initial description, was separated into two units. It was known to be a bipartite package of sediment. And so it was separated into what's known as a lower goiter formation and an upper goiter formation. It appears at least in the Ross River Gorge section that the upper part of the formation is completely missing. It's just not there. When we looked at the isotopic records, it's not there. When we tried to compare it lithologically, it doesn't also compare very well lithologically with the upper goiter formation at the Ellery Creek type section. And so it just appears to be missing in the eastern part of the basin. But in the central part of the basin, it does appear to be there. And following along with an old card, registration card in the paleontology collection at Geoscience Australia, I managed to track down one trilobite species that was recorded from the locality. Just one. It's not much more. It's very, very uncommon to find fossils in this unit. But it seems somebody managed to walk up a creek and find this beautifully preserved head as a series of other bits and pieces, cheeks and a tail and etc. And it's currently unpublished. This is one of the specimens we have. There's about half a dozen others. And it's of a species, a genus of trilobite that occurs in the Georgina Basin in basically what we would consider the middle part of the traditional late Cambrian, if you like, the Irvanian stage. And so we can sort of effectively give the upper part of the goiter formation an Irvanian date. Now, it's a bit tenuous, I grant you that. It's not a definitive proof that the upper goiter formation is of this age. But given other members of this genus all occur at this stage, it seems highly likely that this is strong evidence that the upper goiter formation does sit within the Irvanian stage, and that there is in fact representation of the middle part of the late Cambrian, if you like, in the Amadeus Basin. Now, I mentioned that the Pacoota Sandstone was well studied, and it is. It's very well studied in 1991 by John Shergold. But John Shergold he created three assemblages from the unit. And the first of his assemblages, he gave a very broad age range to. A lot of the species he described were new. And so he sort of hand-wavingly said, well, a lot of them are new. I can't really correlate them. But based on these other features, we can sort of give it a Plantonian or Ditsonian age. So the latest part of the late Cambrian, if you like. But that's not terribly precise. However, based on trilobite material that we also collected in New South Wales, we can actually make this slightly more precise. One of the things that he described was this trilobite species here. This comes from the lower Pacoota Sandstone. I don't know why it's replaced my Y with a comma, but it has for some strange reason. I just noticed that. And one of the species, this species here, is extremely useful for comparison because it's an identical species from the neighbouring part of far western New South Wales. So they're effectively identical in a number of respects. They're not just identical in things like, for example, shapes of the head. They're identical in even things down to like the shape of the ornamentation across large parts of the cranium, large parts of the cheek, and even large parts of the tail. So it demonstrates that this is almost certainly the same species. Now, this is important because if we compare this species from what's known as the Nootumbulla Sandstone, which is this New South Wales unit, from the upper part of the unit, so that was from the lower part, we get that species that's comparable to the Pacoota. The upper part of the unit in the Nootumbulla correlates very well with the Kandie tank limestone, which has conodonts that give us a very, very, very early Ordovician age, as in it sits right on the boundary with the Cambrian Ordovician, which tells us that the lower part of the Nootumbulla must sit at the very latest part of the Cambrian, so what's known as the Datsonian. And so therefore we can be quite precise in saying, well, that trilobite that we're finding in the lower part of the Nootumbulla is Datsonian, or is strongly and highly likely to be Datsonian in age, rather than Platonian in age. The next set of units I'll talk about, I'll skip over the Horn Valley, as I said, was well studied in great detail by John Murray, and the conodonts have been well studied recently by Yongyi Zhen. We'll skip ahead to the Stairway Sandstone and Stokes Siltstone. The unit itself, the Stairway Sandstone, is a thick unit that occurs throughout much of the basin, a bit like the Horn Valley Siltstone that underlies it. And the Stairway Sandstone has had a bit of paleontological history with it. Jacobson and others described a very limited fauna from the central part of the basin in 2014. But most of the species, as you can sort of see here from the list, I've tried to sort of represent the most well-described bits and pieces actually from it. It was very, very poor material, and that's more to do reflection on just how poor the outcropping the unit is. Not a reflection on their efforts. And so what you're looking at is it's largely bits and pieces of bits and pieces. So they're fragments of trilobites. Similarly, the Stokes Siltstone is likewise also very, very poorly outcropping. In fact, the only trilobite that's been known for it was described all the way back in the 1800s, back in 1892 by Etheridge. And in fact, he didn't even figure the real specimen for it. He figured a composite of 7 specimens. So what you're looking at here is really a make-believe specimen. It's not even a real specimen. And in fact, having seen the real material, it's very far from the truth, what you're looking at. So we decided that we would report on trilobites from the lower part of the Stairway Sandstone, because that seemed to be the better preserved material and it hadn't been reported on before. Jacobson et al. Had only really reported on the middle and upper part of the Stairway, as well as the lower part of the Stokes Siltstone, which also hadn't been reported. So you can see there, the lower part, the lower member is right off in the background, is that lower hill there. And then the Stokes Siltstone is largely a scrubbly plain. And so we found quite a diverse fauna. There are at least 6 new species of trilobite in amongst the material. This is just a selection of the material. We also were able to collect more material of the previously described species and place them more correctly in a better known genera, or sometimes in at least more correctly assignable genera for these species. So for example, the Acivus thorntonii becomes Basilicus. The other ones that were assigned to Parabasilicus were placed in Basiliella, things like this. Now, unfortunately, all those species, if they were new or if they were previously only described from the unit, aren't really comparable to anywhere else. And so we couldn't compare them to any other units. However, the conodonts that had been described from the unit, we could compare. And those conodonts seem to suggest a Darriwilian age. So it seems to suggest a middle Ordovician age. So the traditional middle Ordovician. From what's known as the DA2 stage, so sort of the middle of the Darriwilian, if you like. Both the Stairway Sandstone and the Stokes Siltstone seem to sit in this unit. The Stokes seems to push a little bit further into the DA2 stage, but it still sits firmly within that age range. So we can change a few of the dates around. We can add a few more there. We can also separate out two of the assemblages. So we can give the Basileella brumbiensis assemblage, because that's one of the most abundant species that we find. And they can also name an Idorasis schurum assemblage, which is one of the most populated trilobites that we find in the Stokes siltstone. Now, of course, I couldn't not talk about the Stokes siltstone and Stairway sandstone without talking about the species that was mentioned before. This is Lycophoron titan. It was found amongst the Stairway sandstone species. It's a large pygidium, a large tail of a trilobite. So what you're looking at there has a reconstruction to the right of it. And there's a lovely sort of colorized reconstruction down there by Adam Yates down the bottom. And it's a large trilobite that would have been, we think, the third largest species in the world. So it's one of the largest trilobites known globally. It is the largest trilobite known from Australia. It's only a fragment, of course, it's not complete. It's still the largest complete trilobite is Redlickia rex, but it is at least the largest trilobite known from a fragment. It would have approximately reached about 42 centimeters in length. The pygidium itself is roughly about up to almost 20 centimeters long. It's likely that they could have got a bit larger. This is just a sort of an average medium-sized individual that we managed to find, but fragments suggest they could get potentially much larger. Finding that giant, and obviously as Amber said as well, it got in the news, it got in the ABC News. Following the discovery of that giant, it got me thinking about these large trilobites, these large asphids over time. Why do we get so many of these large trilobites, these large asphids in Australia, particularly in the middle of the Ordovician? In fact, if we look, you can see here there's a graph of primitive, what we call Ibexian trilobites versus what we would consider advanced, if you like, White Rockian trilobites, and the number of asphids. And if we look, we can see that the aspid trilobites do relatively well sort of early on. They seem to increase up until about the Darriwilian stage, up until the middle Ordovician, and then all of a sudden they crash right at the sort of transition point between the advanced trilobites decreasing and the advanced trilobites increasing and the primitive trilobites decreasing. Now, if we look, that seems to correlate very well with the tectonic models at the time. So there's the Dullinger and Redingen movements that occur at that point in time. These are basically geological movements that seem to have closed off large parts of the internal seaways, the epicontinental seaways that formed the Australian sort of super basins that formed at the time. And these basins, these internal basins, seem to be aspid dominated. They seem to be dominated by these large trilobites. And as soon as they closed, the island arc trilobites seem to have won out, basically. The aspid dominated trilobites were forced to compete with them. They couldn't compete and they basically died off. And so the only aspids left were the few species that managed to cling on these island arc systems. So if we look at an overview of what we managed to do, we can see here the red arrows indicate what we can basically add in as the new assemblage zones to the Amadeus Basin that have been added as part of the recent work that's been done. The previous work that you can see there is just some of the names given without any of those arrows, as well as some of the work that Yongyi's done with the conodonts in the region. And you can see that we can shift around quite a bit of the stratigraphy of the basin based purely on just the biostratigraphy. We can give a bit more precision into the dating, particularly. We don't just have to use those classical early, middle, and late Cambrian terms. We can be a bit more precise with our language when discussing parts of the stratigraphy of the Amadeus now. So future work can work towards particularly looking for, we have evidence that there's rectocephalid and oranaspid trilobites within the basin. These are great trilobites for dating parts of the Cambrian, particularly the early middle parts, or possibly the latest part of the early Cambrian. These would be great to go off and collect more material of. The other thing as well is that we could look at for things like early Ordovician and the latest part of the late Cambrian conodonts from the Pacoota Sandstone, because whilst they are known, they aren't published. Similarly, the Stairway Sandstone, it would be great to have conodont collections, large conodont collections, that could actually be published from this unit. Because again, they are known from the unit, but they just aren't published, unfortunately. So these are all the people that need to be thanked. There's a large number of individuals that have been involved in this research over a number of years, as well as a large number of organizations that have funded this work. And thanks very much for listening.